Hello, welcome to our presentation. This is Carla Lee from University of Groningen, the Netherlands. I'm going to present our work published in REL with the title Continuous Time Ultra-Wideband-Inertial Fusion. This is joint work together with Jules Hau from Linköping University in Sweden and Will Hannebeck from Karlsruhe Institute of Technology in Germany. Ultra-wideband sensors, they have many advantages when it comes to motion estimation working in the way of sensor networks. For instance, each of the nodes here, they are very lightweight, they are low cost and energy efficient, and they are also very well scalable for large-scale deployment. Specifically, they have very high spatial resolution of impulses up to the level of nanoseconds, and they have been very popular for applications such as indoor positioning and motion estimation, especially for industrial automation. However, there are still many challenges if we want to use ultra-wideband sensor networks for motion estimation in real world. For example, we can easily have unlost effects, we can have multipath conditions, and also the performance could always be scenario dependent. We can have very complex noise patterns because moving objects, especially if the object is of ferromagnetic material, and here in this example, you can see the noise pattern is very complex. They are non-Gaussian and also time variant. In this regard, we recommend this great data set recorded by our colleagues from the University of Toronto. This is a great data set for studying UW localization. Those issues can be mitigated by using multimodal sensors, and here in this work, we specifically look at the possibility of combining ultra-wideband sensors together with inertial sensors. Having the inertial measurement unit on board can give us some advantages. For example, we can have instantaneous and high order motion information such as acceleration and angular velocities. They are both cost and resource efficient, and as you can see in this example, they are well integrable into ultra-wideband sensor networks. And the fundamental task of using multimodal sensor for state estimation is to basically combine the measurements from different modalities of the sensors and deliver an estimate of the motion state at certain time intervals. From a generic point of view, this is actually quite common nowadays for many robotic systems. For example, this is our previous work combining light detection ranging sensor together with inertial measurement unit on board to perform odometry and mapping. And for some other system, it is easy to find, for example, cameras, IMUs, lidars, and even some asynchronous sensors such as event cameras. All sensors they fire at different time instants at different frame rates, and we want to perform estimation also at another set of time intervals. And typical approach would be based on discrete time fashion, which is against the continuous time nature of the spatial motions. This really motivates us to find another mathematical formulation to do things in a physically adaptive manner. We now introduce the quaternion-based cumulative B-splines to represent the 6 DOF spatial motions as continuous time functions. Here the coefficients, they serve as a state, and this is also very efficient for state representation because they are very sparse in time domain. Through these kinematic interpolation equations, we can guarantee inherent kinematic consistency ranging from 6 DOF spatial poses to higher order motions such as speed, acceleration, and angular velocity. This also helps us to fuse the sensor measurements at raw time instance and incorporate sensor noise directly. For online estimation, we perform spline fitting in a sliding window fashion. This is basically nonlinear least square problems incorporating residuals based on the difference between the raw sensor measurements and corresponding interpolated values from the B-splines. The whole spline fitting package is open sourced. We provide analytic kinematic interpolations and Jacobians for solving the problem. This is also a good thing for efficient learning of coefficients, and the implementation is dependency-free and modularized. We introduce Fuse, the spline fusion-based ultra-wideband inertial state estimation, as a ROS package that is open source on GitHub. This is the first continuous time ultra-wideband inertial fusion system, and it is composed of two parts software-wise, one estimation interface doing pre-processing of the sensor measurements, and the other part doing spline fusion that is introduced before. It is very accurate and real-time capable of estimating 6 DOF spatial motions with the possibility of doing online calibration. This means we can calibrate the gravity's orientation as well as transformation between navigation frames and anchors. It is also robust under challenging conditions that we'll cover later. Here are the results that we ran our system's views on the U2 dataset for different constellations of the anchors and also different trajectories. As you can see, our system can deliver very accurate estimates of the trajectory in comparison with the ground truth in red. The fused dataset has overall 79 sequences composing both time difference arrival, ultra-wideband ranging data, and also onboard IMU measurements. We compare our views with a graph-based approach, which is very similar to Ven's model, and also a baseline approach based on ESKF provided by the dataset. So overall, our system can deliver the best results in terms of accuracy and also much better robustness for some challenging sequences. If we take a closer look at the estimated trajectories, we can find out actually the views can deliver much smoother motion estimates in comparison with the other discrete time approaches. This is because the splines, they can inherently guarantee the kinematic consistencies. This can be also reflected in some very challenging sequences where our spline-based approach can deliver much more robust estimates in comparison with the graph-based approach. Also, for UW-only tracking, our approach can deliver smooth motion estimates. However, the graph-based approach, which is discrete time, it delivers zigzag shape of the trajectories, which is physically infeasible. We have also recorded our own dataset incorporating time of arrival data together with onboard IMU readings using our own experimental setups. Here we can see our result is also accurate in comparison with the ground truth recorded by the Vive tracker. Thank you for watching. Please visit our GitHub account for more information, including the open source code and our own dataset.